So this is draft 0 of my March meeting talk. So I would start by, introducing, hi, my name's Maya. This is the properties of hall bars written with a diamond scribe. So, and then take a second to thank the collaborators who are helping us with this project, and then move it into the actual talk. Excuse me. So the goal for this project is to find ways of creating microstructures without using lithography. It can be difficult to make devices on heterostructures, so if there is another way to do it, we want to find out and refine that technique and see if it's viable. So many of the devices created in our lab are using lithography to draw nanowires and other structures like that, but we may be working with thin films that might have sensitive surfaces, so the lithography process could alter the behavior of the material and the device might not always work. So by using a technique without lithography, there is the possibility of creating more permanent and more reliable devices on the sample surface. So it's not a novel idea to use techniques other than lithography when creating devices. A common alternative is laser scribing. So laser scribing has been used to repair defects in thin film photovoltaic modules, which is like solar panels and things like that, or it's also been used before depositing graphene to hone in on that process and make more precise areas of graphene on the surface of a sample. Another possible alternative is diamond scribing, which is the one that we're looking at. So that entails using a diamond tip scribe to gently scratch the surface of samples to create whatever device that we want. Right now I've been working specifically with hall bars. So there are several parameters to consider when using a diamond scribe, such as how deep the scribe mark will go, the pressure on top of the sample, the angle of the diamond tip itself. So those are things that we've been looking at and trying to hone in on and see if we can refine this process into and making working devices. So the things that we're focusing on to make this a viable technique is minimizing the damage to the sample and obviously trying to create a working device. So we're physically scratching the surface of the sample, so physical damage is a serious concern, because if we're not careful, we can really mess up the surface of the sample. And this is an irreversible process, so it's paramount that we refine how we do it so that we don't end up messing up a sample we really wanted to work with. And in order to create working devices, we have to make sure we're making clean lines at a good depth that's not too far into the sample. And we have to properly draw the shape of the device. So if we draw a hall bar whose channels don't really line up, then that might not necessarily work. So then I would show some pictures of our setup. We're using a robotic arm to do the scribing to minimize human error. So we can send SGV files describing the desired shape of our device so that the robot can do it for us. And the diamond scribe we're using, obviously it's tipped with a diamond, so it has that hardness. I don't know the hardness off the top of my head. It's the tip itself has I believe it's a 60-degree angle. Obviously I would double check the details of this. And then we have it mounted to the robot. The robot itself is designed to be able to hold a pen, so we just stick the diamond scribe into the pen attachment and it can hold it and draw like that. So some of the challenges that we've had to face are minimizing damage. Like I mentioned earlier, physical damage to the sample is a serious concern. And the resolution of the robot limits the size of the structures we can create. So the resolution is 0.1 millimeters. So we can only make hull bars that are about 2 millimeters across and 1 millimeter tall, just because of that resolution issue. And the robot itself has a little bit of hysteresis in its movement, so it's not as precise on these smaller scales, which can be a problem for creating a device in the proper shape. Another issue we've had with minimizing the damage is the depth of the scribe marks. So this affects how clean the shape is overall. So I have AFM images of scribe marks on a glass slide versus scribe marks on a sample. The glass slide, it was much cleaner, but the sample, we went too deep, and so it was too deep for the AFM to even be able to process. So that's kind of a worst case scenario. If you go too deep, you can end up with scribe marks that are really, really deep in terms of these length scales. Another challenge we've been working on is developing a working device. So obviously the physical damage to the sample has been affecting us being able to create a working device. So the robot is somewhat limiting, but it's still overall a little better than trying to draw them ourselves, because we can learn the robot's tendencies and that kind of thing, so we can account for them and work on creating cleaner devices. And then another question that we've run into as we're doing this project is, does the sample itself affect whether this process is viable or not? So the samples I've been working on are LTO, STO samples, so we're running into the question of, are there oxygen vacancies in that sample that prevent us from isolating the inside and outside of the hull bar from each other, which prevent us from creating a working device? So that's something else that we're looking into. And then if I do have time to get data, I would spend a little time showing some data and seeing what we've seen. Also, I don't know if I should have like improvements to be made, because I feel like I might have already covered that. Maybe just like a recap of the challenges we faced and how we want to fix those problems. And then to close, just talking about the future contributions for Oxide electronics. As I mentioned at the beginning of this talk, creating devices on these heterostructures can be very difficult, and it is really appealing. The idea of creating a new technique that will work and is reliable is very appealing. It has the potential of making devices that are more reliable and a little more permanent, since we're physically scratching them into the surface of the sample. And we're hoping to develop this technique in order to create devices in the future.